It's my pleasure to share our recent work here. So today I'm gonna talk about private specification for matrix mechanisms under streaming differential privacy. But rather, the title of this talk should be a review of matrix mechanism under streaming differential privacy. So I think this is a nice work in DP and a little bit underrated. So I wanted to use this opportunity to bring this topic, to bring this line of research to your attention. So I will be more like reviewing this line of research instead of introducing our new result. And in the end, I will probably spend like 15 minutes to talk about our contribution in this line of work. And our main contribution in this line of work will be more about privacy amplification for random sparsification. And this part of work is a joint work with a bunch of amazing people from Stanford and Google. Yeah. Okay, great. And if you have any question, please interrupt me. Please just stop me and then ask questions. Yeah. Okay. So let me start with a quick recap about differential privacy. So this is a basic definition of differential privacy. It's defined with respect to a randomized algorithm A. By the way, you can see my cursor, right? Okay, great. So it's defined with respect to a randomized algorithm A, which takes a data set X as input and output something. And differential privacy basically requires that the output of A, if we replace one entry of X, the output of A, the distribution of output of A will remain roughly indistinguishable. So yeah, and there are two parameters, epsilon and delta, that specifies how indistinguishable the output distributions are under X and X prime. So we will call X and X prime two neighboring data sets if they differ at only one entry. In this case, it will be Xi and Xi prime. Yeah. So the philosophy under differential privacy is that we are gonna ensure safety under the worst case scenario. So you can imagine an adversary that has arbitrary amount of site information. In this case, the adversary knows every entry in X except for the ith entry. And with all of this site information, and it tries to distinguish, it tries to infer the ith entry from the given output of A. So the definition of differential privacy basically suggests that even with this arbitrary amount of site information, the adversary still cannot distinguish between X and X prime. It still cannot make any inference at the ith entry. So a few important properties of differential privacy include the preservation under post-processing. So if you have another function, on this A of X, the output of this function will still be differentially private. And also composition. So if we have two independent DP mechanisms, F1 and F2, then their joint output, if we observe both F1 and F2, their joint output will still be differentially private with a weaker DP parameters, like epsilon 1 square plus epsilon 2 square, and take a square root, something like that. And the canonical mechanism to ensure differential privacy is this Gaussian mechanism. So to introduce this Gaussian mechanism, we have to first introduce the idea of sensitivity. So we say a function f has sensitivity c if for any two arbitrary neighboring data set X and X prime, the difference under L2 norm is at most c. So to ensure differential privacy, if we want to release a differentially private copy of f of X, then we can just add Gaussian noise to the output to f of X. But the key here is that we have to calibrate the noise according to the sensitivity of the target function. So we will set the variance sigma squared to be greater than something like C squared times some function of epsilon and delta. Again, C squared here is the sensitivity of it. Yeah, so this is the canonical mechanism for DP. So the previous Gaussian mechanism is like a canonical mechanism for arbitrary DP task. Like if you want to do analysis, if you want to do any kind of task, statistical task. For learning, the fundamental building block will be this DP-SGD. You probably have already heard of this. Yeah. So DP-SGD, the idea of DP-SGD is actually pretty straightforward. So each step, we will first compute the per sample gradient GI. And then we will do gradient clipping. We will clip GI to make sure its L2 norm is not too large. This step is aimed to control the L2 sensitivity. And then we will compute the mini batch gradient. Basically, it's the sum of individual gradients. And then we add Gaussian noise. Again, the variance of this Gaussian noise will be calibrated according to your L2 gradient clipping norm. Yeah, so this is just the invoke of Gaussian mechanism. So this procedure basically ensures epsilon delta DP each round. So this is only the per round DP guarantee. In the end, we still have to use composition theorem to account the final privacy budget. And a very important intermediate step is that we need to use privacy amplification by subsampling to achieve state-of-the-art DP guarantee. So basically, this privacy amplification by subsampling is as follows. In each round of SGD, we are basically doing mini batch SGD. So we will select a batch, a subset of samples, training samples, uniformly at random. And if we take this random subsampling into our privacy analysis, we can actually amplify privacy to get a better privacy guarantee, better than this epsilon delta. Indeed, if we do this random sampling for m out of n samples, then the above guarantee can be amplified to something like m over n times epsilon. Yeah, so this will be much smaller than the original epsilon and delta if your m is much smaller compared to n. So if you combine this privacy amplification by subsampling, then you will be able to achieve a much better DP guarantee. Yeah, as I said, in the end, we have to do composition for every training rounds. So these are the basic procedure for analyzing DP-SGD. So how can we improve, or what do we need to improve upon for this DP-SGD? First of all, in order to achieve state-of-the-art result, we have to rely on random subsampling. But this may not be feasible in many practical scenarios. For instance, if your samples are like coming sequentially, then you may not be able to do this random sampling. Imagine that you're like a large company like Facebook or Google. Their samples are actually coming sequentially every day. So they have to update their model after like a period. In this case, you may not be able to use privacy amplification by subsampling because your sample is not like offline. Or in some other settings like federated learning, each client may check in your training round randomly. In that case, you also cannot apply this random sampling stuff. So this is one issue. If we didn't rely on this privacy amplification by subsampling, then the privacy guarantee will be much worse. And the second issue is that the previous DP-SGD mechanism is designed with respect to minimizing the per run error instead of the total error. I will be more specific at this point, but you can imagine that here in DP-SGD, we are trying to, in each run, we are trying to minimize the noise adding at this mini batch gradient estimate state, right? So in other words, we are approximating this entire training algorithm by this per run gradient estimate task. So we are approximate it by a mean estimation. But this may not be optimal because we are just like minimizing the per round error. So motivated by these two examples, but motivated by these two issues, later at Google, they proposed a new framework to replace DPSGD. And this framework is called DPFTRL. So originally, this DPFTRL algorithm is proposed in order to address the subsampling issue in federated learning. So they proposed something based on tree aggregation. But later, they observed that even compared with the offline setting, sometimes at certain regime, this DPFTRL can still outperform DPSGD with subsampling. So they kind of try to explore more, and they propose a more general framework, which is matrix mechanisms. And with matrix mechanisms, they can actually prove that it will be at least as good as DPSGD. And sometimes, actually a lot of times, it's even better. Yeah. So after that, there are like a few papers that make significant progress on this line of research. So I will quickly walk through this new progress, and then in the end, I will talk about our result for compressing matrix mechanisms. Okay, great. So now I'm gonna talk about the basic DPFTRL algorithm based on tree aggregation. But before that, let me just quickly recap this DPSGD. So for DPSGD, as I said, in each round, we will update the gradient by, we will update the global model, the model by a noisy gradient. So let me use this capital G to denote the mini batch gradient at round T. Then DPSGD can be viewed in the following way. So for W1, we will update the model by adding the gradient computed with respect to the initial model. And then for W2, we can write it as G1 plus G2 plus noise. And so on and so forth. So for WT, it can be written as a prefix, it can be written as a sum of G1 to GT plus noise added at each round. So if you look at this expression, you will realize that the only part that depends on the private data is this gradients G1 plus G2 and G1 plus G2 plus G3. So in other words, we are gonna do a private release on these prefix sums of gradients. Okay, so for DPSGD, it's more like we are doing DP for each individual gradient. We will get a differentially private gradient estimate. And then we use it as an estimate of these prefix sums. So yeah, one caveat here is that you have to be aware that these GTs are chosen adaptively. This means that, for instance, G2 will be a function of G1. It will depend on actually G2 will be a function of G1 hat if you train with DP. And similarly, G3 will be a function of G1 hat plus G2 hat. So everything is adaptive. This will be like a key point later when we try to do some extension. Yeah.
So sorry, I have a question over here. So here you are assuming that the learning rate is not changed during each step, right?
Sorry, second.
Here you assume that the learning rate is not changed for each step.
Yes. The learning we're using constant learning rate, but this can be extended to with momentum or something with different learning rates.
Okay.
Here, this is just for simplicity. But
okay.
So as I said, for DPSGD, we are trying to minimize the estimation error of each gradient per round gradient. And for DPFTRL, we are doing something slightly different. So let me use this S1, S2 to denote the prefix sum up to round T. Then DPFTRL tries to directly estimate the prefix sum, the prefix ST. So the goal here is to minimize the cumulative error ST hat minus ST. So they have a slightly different target. And turns out if you can obtain an upper bound on this cumulative error, then you can prove some like theoretical guarantee for some online convex optimization. You can bound the regret. And then if you apply some sort of online to offline conversion, you can get another bound for offline setting. And in their paper, they basically show that this offline setting, the error for this offline setting is otherwise optimal up to some logarithmic factor. So this means that theoretically, it's not worse than DPSGD. But practically, we observe that it's actually better than DPSGD. Okay, so now I'm gonna talk more details about how we can design this prefix sum algorithm, differentially private prefix sum algorithm. So for simplicity, let's first assume each GT is a scalar in some bounded domain 0, 1. And also each GT only contains one sample. Basically means that the mini batch size is 1. And these two assumptions are without loss of generality. Because first of all, if we have a vector gradient, then we can just do composition across dimensions. This is like a very standard trick. And then for larger mini batch, it basically only change the sensitivity. So so we can just basically, for simplicity, we will just make this assumption. Okay, so now our goal is to differentially privately release these prefix sums. Then the first attempt will be using vanilla Gaussian mechanism, right? This is just like releasing a t-dimensional vector. So why not just adding isotropic Gaussian noise? Well, the thing is, if you do this, then you have to first analyze the sensitivity. The sensitivity of this one will be actually pretty large because if we change G1 to G1 prime, then in the worst case, it will change the entire prefix sum, by root t. So the sensitivity of this prefix sum is actually root t. So this means that the variance of your Gaussian noise will have to be omega of t. Yeah, this is a typo. It should be linear in t. And the overall MSE will be something like t squared. It's pretty bad. Now, sorry, any question? Okay, so now we can do something smarter. We can use this tree aggregation idea. So here, first of all, we will have separate gradient estimate for each individual gradient. This is like DPSGD. But in addition to this individual gradient estimates, we also construct this binary tree. So for this binary tree, for instance, for this node, we will also obtain an estimate for G1 plus G2. And for this one, we will get an estimate for G3 plus G4. Yeah. And for each node, we will add an independent copy of Gaussian noise. So for each node, they have sensitivity 1. And once we obtain this DP tree, then we can think about how to do this prefix sum estimate. For instance, if we want to estimate S5, then what we can do is we can use this node, the blue one, plus this gray one. Then in this case, we only need to the number of independent noise will only be 2. And if we didn't do this tree aggregations trick, then we have to sum over G1, G2, G3, G4, G5. It will be 5 noise random variables. So doing this tree aggregation trick allows us to reduce the noise by a lot. Of course, you can do some simple calculation. For each prefix sum, you will need to aggregate at most log t nodes, right? So the number of additional noise will have another factor of log t. Also, the L2 sensitivity for this prefix tree is also log t, because each gradient gi will be included in at most log t nodes. So doing this tree aggregation trick, the total MSE can be reduced to something like t times log t squared. This is much better than the vanilla Gaussian.
Sorry, I have a quick question.
Yep.
So does that mean in practice we have to store these tree of gradients in
That's a
order
very good
to?
question. No. Later, after I introduce a more general framework, you will see that the only thing we need to store is this noise, or you have to compute this noise in a certain way. You don't have to store all of these intermediate states. Yeah, but even if you store everything here,
we will sample. We will store a tree of these noise, right? That's the.
actually no. Yeah,
No.
we will see later. But that's a good question.
Okay.
Yeah.
Okay.
It's a special case of matrix mechanism, so you can do it in a matrix mechanism way. And turns out the only thing you need to do is to color this noise. You have to generate correlated noise in a certain fashion. Yeah. So in this case, yeah, maybe it's not that obvious, but later you will see that we can do it in a very efficient way.
Okay.
Yeah, I also have a question over here. Maybe I misunderstood something. So for the vanilla Gaussian, that part, why the second step we are trying to release the G1 plus G2? Why not we are releasing G1 2 plus G2? The first step we already add noise, right? Then why we still release the raw gradient over here?
You mean this state?
Yes.
Yeah, this statement is more like it's more. If we go back to this SGD setting, more like when you try to compute all of these model weights, it's equivalent to release this G1, G2, and G1 plus G2, all of this stuff, right? I guess all you are saying is more like if we only have access to this G1 plus N1, then why do we need this step? Is that?
No, I mean, when you apply DPSGD, when you do the first round, you got the real gradient and you clip it, you add a noise, then what you already obtained, the gradient is already adding added noise. Then you go to the second round to calculate the gradient. Then why we expose the based on the yeah.
So the thing is, this is not DPSGD.
Okay.
This is a new algorithm we proposed.
Okay.
So for DPSGD, you are right. We are adding like per round noise. We're adding per round noise like this one. So this G1 hat will be G1 plus N1, and this and the second step here will be G1 plus N1 plus G2 plus N2. You are right. But the algorithm we propose, the vanilla Gaussian mechanism, is not DPSGD. DPSGD can be another option, but you can also like do the calculation very quick. Like if you use DPSGD, we will have like independent noise at each round. Then in the end, the cumulative error here, the cumulative MSE will be even larger. Like if you look at the final step, it's like G1 plus N1 up to GT plus NT. So the variance of your noise will be something like t squared.
Okay, got it.
Yeah.
So this new algorithm is that we actually, for each step, we accumulate the gradient. Then we add the noise on this accumulated gradient, like from
Yes.
all the previous steps.
Yes.
Okay,
Yes.
got it.
It's about how we can differentially private reduce the entire prefix sums.
Okay, got it.
Yeah, DPSGD is one way, but this is not the way we propose here. So this is conceptually, this is how we can compare DPFTRL and DPSGD. For DPSGD, the per run noise is smaller. So we would expect like smaller deviation in the beginning in each per run estimate. But because the noise is IID, so they can accumulate pretty fast. So in the end, we may arrive at like a farther point compared to the actual optimal one. On the other hand, for DPFTRL, the per run noise may be larger, like large by a factor of log t or something, log t squared. But it's optimized with respect to the cumulative error. So in the end, we can achieve a closer point. And of course, this is just a conceptual understanding of two algorithms. This is not a rigorous proof because here we assume every updates are non-adaptive. But for our DPSGD, for our optimization case, they are actually adaptively chosen. So yeah, this is just a conceptual understanding. Now, going back to our tree algorithm, we say that if you want to estimate S hat 3, what we can do is we can use this node plus this node, right? But this is not the only way to estimate S hat 3. Indeed, there are multiple ways. We can also use G1, this G1 hat plus G2 hat plus G3 hat to estimate S3. This is just like SGD. This will give you a larger variance, but it's also an unbiased estimate. So you can also do something fancier. You can do this using this node to minus this node. This will also give you an unbiased estimate. And indeed, you can do some linear combination of all of these estimates. And how to get the minimum variance? This is actually a well-studied problem in differential privacy literature. They basically show how you can combine all of these estimates and make an efficient use of this DP tree. But turns out not all of these estimates are differentially private under adaptive setting. So here's an example. If you look at the last case, if we try to estimate S3 by using the root node minus G4, then this will be some issue if GT are adaptive. Why? First of all, S3 now depends on the noise of the last node of G4. It turns out this G4 is also a function of your S hat 3. This means that now this G4 is a function of its own DP noise. So this will cause some problem. You won't be able to get any DP guarantee in this case. So if your GT are non-adaptive, then it's fine. But for our optimization problem, GTs are actually adaptive. We cannot directly use this approach. So in this paper, they basically propose two different types of estimate. One is the online estimate, which basically means that if you want to estimate ST, you can only use nodes before T. And the second approach is called full tree estimate. So for the full estimate, you can use the entire tree, and the full estimate only hold for the non-adaptive setting. It turns out the full estimate is actually way better than the online estimate. So this seems to suggest that there's a strict separation between adaptive and non-adaptive settings in terms of prefix sub continual release. So in order to further improve the previous tree aggregation mechanism, we can study a more general framework which is called matrix mechanisms. So the idea is as follows. Now our goal is to release these prefix sums in a differentially private way. This can be written in the following metric form. We can write it as a lower triangular matrix A, multiply this gradient vector, G1 to GT. And then our previous vanilla Gaussian mechanism suggests that we can add a isotropic Gaussian noise here. But this will be suboptimal because the sensitivity of this prefix sums is actually too large. And the sensitivity of S can actually be written in the following way. It can be written as the sensitivity of A times the sensitivity of G, where the sensitivity of A is defined as the maximum L2 norm of the column in A, right? So now how can we improve this approach? Well, the idea is that we can if we can factorize A into B times C, then we can just add dp noise to ensure CG plus Z tilde is dp. And then this, the multiplication of B can be viewed as a pre-processing of the entire mechanism. So now our goal here is to only ensure CG times Z tilde is dp. So we can formulate this as another optimization problem where the goal is to minimize the Frobenius norm of B times sensitivity of C subject to BC equals to A. So the objective function in this minimization is basically the final MSE, right? The final MSE will be the sensitivity times the Frobenius norm of B. So it's like we are trying to minimize the MSE. And turns out this optimization problem can be reparameterized as a semi-definite programming problem. So it can be solved efficiently. And also, what's even better is that if you look at this algorithm, what we actually need to do is to replace the independent noise N1 to NT with this correlated noise. And the correlation is basically characterized by this B times Z. So to answer Eli's previous question, we don't need to change our training paradigm. The only thing we need to change is the way we generate noise. We only need to generate correlated noise in this way. So this is kind of like very elegant, right? So we don't need to do anything except that we add some correlation to our dp noise. This will give us a huge improvement. Yeah. So still, we haven't resolved the previous adaptivity issue. And this is the main contribution in this paper. So basically, they show that as long as the noise mechanism is Gaussian noise, then if the previous matrix mechanism satisfies non-adaptive dp, it also satisfies adaptive dp. So turns out the Gaussian noise is a key in proving this theorem because we need to make sure the entire noise mechanism is rotationally invariant. So the key step is to leverage this rotational invariance. Yeah. So in the previous tree algorithm I introduced earlier, for a non-adaptive setting, it can be used with arbitrary dp mechanism. The noise does not have to be Gaussian, but for the adaptive setting, you have to use Gaussian noise. And then another remark is that tree aggregation can be viewed as a spatial case of matrix mechanism. It's like you are building this matrix according to this binary tree. So tree aggregation is just a spatial case. And finally, this framework can easily incorporate momentum. The only thing you need to change is this target A matrix. It will still be a lower triangular matrix, but it will no longer be this O1 matrix. It will add momentum term in the coefficient. Yeah, so here's a figure about the performance of different prefix sum mechanisms. So this online and full are basically the two tree aggregation mechanisms I introduced previously. And both of them are much worse compared to the optimal prefix sum matrix factorization. Yeah. Okay, so I guess I'll pause here and see if there's any question regarding this matrix mechanisms.
I have a question. So for the sentence that say if the matrix mechanism satisfy non-adaptive DP, it also satisfy adaptive DP. Does that mean like whether these matrix mechanism is adaptive or not depends on how we factorize the matrix A? Is that correct?
Yes, we to factorize A optimally, it does not rely on whether GT are adaptive or not.
Okay.
Is that your question?
Yeah. So my next question is actually like maybe partly related to what Houghton just asked, is like whether GT depends on, let's say, GT minus 1. So you're saying in your previous slides, those GT can be a function of, let's say, GT minus 1 up to G1.
Yes. GT will be a function of S hat T minus 1.
Oh yeah, after adding nodes.
Yes, yes.
I see.
Yeah, I mean, if you have like arbitrary adaptivity, then it's likely this type of factorization may not be optimal, because if you have some adaptivity, you can maybe construct some pathological case such that adding this type of noise is not optimal. But for like independent gradient or like independent non-adaptive GTs, this approach is optimal.
Yeah.
I guess I'm just trying to say that adaptivity does not change your privacy guarantee, or does not change the way you factorize the way you factorize these matrices. It could only change maybe the empirical performance, only change the utility.
I see.
Okay, so
Wei-Ning, I just have first, sorry for being late. I was in a call. Like, thank you for coming to our group meeting to give us this. So this is a really nice talk. So I have a question. Like, so is there any example for that particular A that like this triangular matrix? Like, what's the optimal B? Is there a closed form solution?
That's a good question. No, there's no closed form solution. I should have put the example B matrix here. It looks like, I don't know how to say that, but it looks like some banded matrix where it will have values in like this part. So it's like periodic like value. But you can go to their paper and then they actually do some visualization of the matrix B. It's not like simple linear algebra will give you the optimal one. It's actually non-trivial and does not have closed form solution.
And also, this is more like sorry, I missed the first part of your talk. I think what you mentioned here is more like a general mechanism. So basically, I can have arbitrary A, right? As long as it's a linear operator or like a matrix, then I can do this factorization too. Is this the idea behind, like the key idea behind this?
Yes, but it has to be lower triangular for causality, right? Because you have to, it has to be causal.
I see.
Yeah, but it can be arbitrary lower triangular metric. You are right. Like if we we can incorporate with like different learning rates, or we can incorporate momentum. The only thing you need to change is A.
I see. This also not necessarily correspond to the, let's say, the gradient descent or subgradient descent you mentioned. So my feeling is even in this way, like the lower triangular, even we do the let's say language model inference. Yeah, that's also causality. When we predict the next token only depends on the previous tokens. But I'm not quite sure whether we need to keep private like with respect to each token there. But I think this is a very, very general like a mechanic, let's say general like a setting that not only for the gradient descent type of optimization.
Yes, you are right. Actually, like in DP literature, this type of problem has been studied like for a long time. You can view like the first paper that systematically study this tree aggregation approach is like it's like 2015. It's like several years ago, 2015.
I
so
see.
This problem has been encountered in DP for a while. But previously in like non-learning setting is less adaptive. So they don't consider like adaptive setting. So it's until recently when they try to apply this kind of approach to learning, they have to develop something new to handle adaptivity. But you are right, this is like a very general framework, general problem in DP.
Okay, thanks.
And maybe one more thing I wanted to mention is that this factorization does not depend on the problem dimension. So let's say if you have fixed training round, let's say we want to train with 512 rounds, then you can do this factorization once. Then this optimal matrix B and C can be reused like for different applications. Yeah, so this can be generated offline. Once you compute the optimal B and C, you can store it and reuse it for different applications. Okay, so in the last part, I wanted to talk about privacy implication by random sparsification in these matrix mechanisms. So in practice, like memory and communication cost is usually a bottleneck for training large models. So ideally, we want to compress local gradients, and hopefully we don't hurt the performance by too much. And indeed, if we also care about differential privacy, a lot of time we can actually achieve compression for free. So the idea is that with differential privacy, everything now becomes lossy. So you will lose some information for your local gradient. And if you do your compression in the right way, then you don't have to suffer from double penalty. So one of the very useful approaches to do gradient sparsification. So this is like a rough steps for gradient sparsification. So let's say we have a local gradient, which is nothing but just a d-dimensional vector. Then we do the sparsification in the following way. We generate some IID mask where each element in MI will be an independent Bernoulli random variable with rate gamma. Then the mechanism is as follows. We will random sparse each local gradient according to mask MI. And then we compute the average. And then we add Gaussian noise. And turns out, with this approach, you can amplify differential privacy. Because if you look at each coordinate of this gradient, it can be viewed as a random subsampling. So you can apply privacy amplification by subsampling and then do accounting across privacy accounting by composition theory across all dimensions. Of course, like if you want to get tighter privacy guarantee, you have to do something more, but this is a rough idea. We treat each coordinate separately and then apply composition theory.
I have a quick question. Sorry for interrupting. But like in DP, shouldn't like for our adjacent data set, we are either adding or removing a point or say replacing a point, right? So it's like we are changing the whole gradient vector GI to some other gradient vector GI prime. Right? So shouldn't, like in the worst case, we will, like all the gradient could be concentrated in one coordinate.
That's a very good question. Yes. But there are a few ways to resolve it. First of all, you can do some pre-processing like random rotation or some flattening with respect to some fixed linear transform. Then in that case, you can flatten your gradient. So essentially, you will get an L infinity bound on your gradient vector. This is one thing you can do. And then second, even all of the energy of the gradient concentrate at a specific coordinate, this approach still work. For instance, if you do this IID mask for that specific coordinate, it can still be viewed as random sampling, right? You just randomly drop that coordinate, certain probability.
Okay.
Yeah, but like flattening does improve like second order term. So in practice, we will still do flattening step. You're right. Yeah.
Thank you.
And turns out if you combine privacy amplification, you can do a pretty aggressive sparsification. Like as long as your sparsification rate is not ridiculously high, you can get an MSE that almost match the uncompressed Gaussian mechanism. Okay, but everything I talk about sparsification now is only for DPSGD. It's not for matrix mechanism. So if you want to extend this idea to matrix mechanisms, there will be some issue. So as I said, in DPSGD, the sparsification is basically done by coordinate-wisely subsampling. And in that case, coordinate I is independent with coordinate J. So we can analyze them separately and then apply privacy amplification by subsampling. But for a matrix mechanism, this fact does no longer hold. Why? So if we look at this one, if we try to replace G1 to GT by the sparsified gradients, then if we look at the first sparsified gradient, turns out its J's mask will affect S2 to ST. This is because now this G1 will appear at all of the subsequent rounds. And also because this M1J affects S2 to S3, not just at the J's coordinate, but the entire gradient. So it will introduce both spatial and temporal couplings. So we can no longer do the same analysis as our like previous DPSGD setting, where basically we rely on strong composition. So in this paper, I'm not going into the detail, but in this paper, we propose a new reparameterization of this matrix mechanism. And the conclusion is that the same privacy amplification applies for Bernoulli sampling and Gaussian noise. So as long as you do this sampling in an independent way, then you can still enjoy the same level of privacy amplification. This is our like main contribution. And yeah, practically we can also observe some non-trivial compression rate, like up to maybe 100x compression. However, I have to say that for this DPF-TRL type optimizers, it's actually less compressible. Because for DPSGD, we can compress even more aggressive, like 1000x. But for DPF-TRL, we can compress at most like 20 to maybe 100x. Yeah.
So here, like 100x means the Bernoulli you drop with.
Yes, gamma is
only
like
keep
0.01.
Yeah, so it's like out of 100 you drop 99 of them.
Yes, it's like this gamma, this Bernoulli mask is 0.01.
So even we drop, like we only like keep 1% of things, and we can still have a good test accuracy. Is that what?
Yes. That's pretty surprising, right? I mean, when I did experiment for DPSGD, I was also very surprised too. Like we can drop out a lot of coordinate while still maintaining good accuracy. Yeah, I guess the idea is that if you analyze the error due to compression and compare it with your DP noise, they are actually at the similar order. Yeah. So if you think in this way, maybe it will be more reasonable.
So it's like if we drop more, then we can lower the Gaussian noise, something.
We will reduce the Gaussian noise.
Yeah.
Okay, so these are pretty much all I wanted to share. And there are some recent advances for a matrix mechanism. One of the drawback for matrix mechanism is that it only applies to single epoch mini batch SGD. In other words, when you train with matrix mechanism, you have to do shuffling and then mini batch, and then the mini batch, the batching has to be without replacement sampling. So you have to like finish one entire epoch and then go to the other epoch. You have to do this. You cannot do sample with replacement. And in recent work, they try to improve on that. So yeah. So they first proposed something called banded matrices. So they restrict their factorization into a certain type of matrix. And then in this case, they can allow multi-epoch participation. Basically, this banded matrix, the idea behind this banded matrix is like each client will participate. When one client wants to participate the entire training, it will have to wait until a certain time period to enter again. This is called the banded matrices. And also recently, they proposed another privacy amplification by subsampling. This allows multi-epoch participation, but it only holds for epsilon delta DP. Yeah. So I guess I will stop here. And these are the main references I cover in this talk.
Wei-Ning, would you mind sharing this, let's say send this share this slides with us so that we can have some further learn like studies on this. Thank you so much.
Yeah.
Yeah, Wei-Ning, I have one question because you mentioned this single epoch. As far as I know, right now the most like large language model pre-training right now, they are just a single epoch. Because just like the data set is so large, I was wondering whether is this when people, let's say, bring this, let's say, matrix mechanism like up like very recently, is this there a goal that is trying to leverage it to, let's say, leverage this mechanism to the into the like language model training or something?
I would say, unfortunately, because currently I don't think we can train or we can pre-train language models in a differentially private way. The noise is just hurting too much for large models. Typically, like DP only comes into play for the fine-tuning step. You have to combine it with like LoRa or other technique for fine-tuning.
I see.
If you want to pre-train a large model from scratch with DP, I don't think there's any good result yet. Yeah, I'm not sure
Uh-huh.
if it's even doable or not. Yeah.
I see. I see.
So originally, this metric mechanism is proposed like under an online setting. That's why they only consider a single epoch setting. Yeah.
Okay.
And it's kind of the limitation, and I would say very hard to get rid of.
I see. I see. So another question for this is maybe I missed like some of the comparison. So if we just if we leverage this method with if we compare this method with very standard like a DPSGD method, well, how much improvement we may expect? For example, like regarding the added noise or do you have any let's say high level understanding that can let us know?
Yeah, in terms of accuracy for like training smaller model, like a few million LSTM model or some maybe simpler CNN models, the improvement upon accuracy is like a few percent. I would say like 3 to 4%. It's not huge, but we did see like consistently improvement.
Or let me ask in this way. So but I guess when you compare their utility, it's more like we have the same privacy constraint. We have the same like epsilon delta. So let me think, how can I say this? So I just would like to understand regarding the noise that we want to add there. Let's say
you are thinking about like MSE, or is that like the variance of the noise, the equivalent noise?
Yeah. Kind of. Yeah. Kind of what's the scale? Is the scale will be different or yeah?
So otherwise, I think it will be the same. But it's not I would say it's not an apple to apple comparison, because for matrix mechanism, what we care about is the cumulative error, right? It's not per epoch error anymore. So as I wrote here. Yeah, sorry. What we care about now is the cumulative error on the previous side. While DPSGD is more like we are optimizing with respect to the per run gradient estimate. Yeah. If we compare with the per run estimate, then of course DPSGD will be better. But if you compare with respect to this cumulative error, then DPFTRL will be like way better than DPSGD.
I see. I see.
So it's kind of hard to tell in terms of MSE which one is better or which one is not.
I see. Oh, okay. So this is why this setting right now is more let's say more kind of proposed for this online setting. So basically we not only care about like the final thing, but we also care about like all the intermediate state, right? So is this yeah, okay. I see.
I would say one of the main difference between DPFTRL and DPSGD is the like different objectives. For DPFTRL, it's more like we are planning for the entire training run. But for DPSGD, we are just optimizing with respect to the per run.
I see. I see. Okay, got it. Thank you.
Yeah, I have one more question regarding the coordinate subsampled Gaussian mechanism. So here, so if we compare with the DPSGD, basically they're going to sum over the gradient within the batch. Then we add the noise, then we calculate the average. But I observed here is that for each gradient, you element-wise times or mask, then do the average, and later you add the noise. I just curious the difference, why it happened in this case. Yeah.
For DPSGD, we are also first calculate the average and then add a noise. It's like this is more like a mini batch. Like I'm not sure if I'm looking correctly, but yeah.
Yeah, so basically we are doing the sum over, then we add the noise, then we took the average of the samples within the batch.
Ah, I see.
Yeah.
It doesn't matter. I mean, it just yeah, it doesn't matter. So for SGD, it's more like we take the sum and then we add noise and then we normalize it. But
Yeah.
because of this normalization factor, your sensitivity will be changed accordingly. So
Okay.
so it does not matter
So-
whether you do the
So basically later when you do the calibration, you need to you also consider how to calculate the sigma, like how much variance you're going to add it corresponding to. Okay, got it.
In this case, the sensitivity will be something like 1 over n times gamma. We'll have a term related to this normalization term.
Okay, got it.
Okay, if no further question, I guess I will just stop here.
Thanks for the great presentation.